In 4.2, we are going to look at the quantum model of the atom. Up until this point, we have thought that there is a nucleus with the protons and neutrons in the nucleus, and then the electrons are orbiting around that like planets orbit around the sun. And that's pretty much where junior high models stop when they talk about an atom. So now we're going to be going a little bit deeper into the understanding of what an atom actually is like. So one thing to keep in mind, if we look at the periodic table, one thing that we talked about in the last chapter is every time you increase to a new element, we're adding protons, but if that proton is neutral, we'll be adding electrons as well. So if we start out with hydrogen, we should have 1 electron, and then helium should have 2, and lithium 3, beryllium 4, boron 5, and so on and so on. So as we're doing these models, we are looking at basically where are all the electrons placed as we add additional electrons as we move through the periodic table. So keep that in mind. So keep in mind we have this order throughout the periodic table. First of all, Heisenberg's uncertainty principle. And if you're a fan of Breaking Bad, you might have heard of Heisenberg. That was his name, his nickname. And so Heisenberg's uncertainty principle says that we cannot know at the same time where an electron's located and where it's going, because electrons are so small, so that if we were able to detect where it's located, we're going to throw it off course basically of where it was going. So we can't know those two things at the same time. And so if you think about the Breaking Bad show, the guy was on the run all the time. So that was a good nickname since he was a chemistry teacher. And so if he understood this principle, it's like he's evading the law because they won't know where he's at or where he's going. So electron, it's a proton. Where are you? Oh, that's a toughie. Yeah, I can tell you where I probably am. Does that help? So that's supposed to go with that Heisenberg's uncertainty principle. So quantum theory, basically, we're going to use numbers to map out where all of the electrons are. Just like if you had a map and you were looking for a location using latitude and longitude, you would have numbers to tell you where something was located. Here, we're going to use numbers to tell where electrons are located. Another new concept is the concept of orbitals. In the last chapter, we talked about the electrons are in orbit around the nucleus. So that was a specific path. Now we're looking at orbitals, which are regions or areas where they're most likely going to be located. So this is an area as opposed to a path. So when we talk about quantum numbers, these are those numbers that are going to identify where the electrons are located, like the latitude and longitude. Now we're going to have a set of 4 numbers to tell us where the electrons most likely are to be found. So those numbers are going to tell us 4 things: the energy level, the shape of the area, the shape of the orbital, the orientation, how it's turned, and the state of electron. Which way is that electron spinning? So this is kind of a map of what we're looking at. First, we'll determine the shell, or the energy level. Then we'll determine the shape, how many different shapes we can have, and then the orientation, or the spin. Is it spinning positively or negatively? So the first quantum number is called the principal quantum number. This is the main energy level. So in past models where you have the nucleus in the middle and then different levels or rings around that nucleus, this is basically what they're talking about. And the symbol for the principal quantum number is N. So if N equals 1, that's the first energy level, or sometimes we'll say shells or energy shells. If N equals 2, that's the second level, and equals 3, that's the third level. And we can use the level to determine a couple different things. First of all, how many orbitals can be in that energy level, and we're going to use equation N squared. And then the next one, we can figure out how many electrons will fit in that energy level. And for that, we're going to use 2n squared. So let's say we're in the second energy level, where n equals 2. 2 squared, 4, tells us that we can have 4 orbitals in that level. And then n squared times 2, or 8, we can have 8 electrons in that level. So here's what we're talking about to give you a visual. So if this is the nucleus, the first energy level, n equals 1. The second energy level, n equals 2. And so instead of staying on that purplish line, now we're saying that the electron can be somewhere in this area. So let's say if n equals 4, instead of staying on the fourth ring, now it means it's somewhere within that fourth area. And then if we look at how many orbitals, so if we're in n equals 3, within this third ring, we can have n squared, or 9 possible orbitals, or possible areas. And then how many electrons? 2n squared, so 18 possible electrons in that third area. The second quantum number is the angular momentum quantum number, or the symbol for this is L. And this is the shape of the orbital, or the shape of the area where the electron is most likely to be located. And so the possible shapes that we'll have are going to be equal to the n value. So if we're in n equals 1, or the first energy level, we will only have one type of shape. If we are in n equals 2, or the second energy level, we can have 2 possible shapes. So when we're looking at shapes, these are the shapes that we're looking at. And so the first one is called S, and then P, D, and F. So those S, P, D, and F are the names or the symbols for what those shapes look like. So we look at the first shape, S. It's a sphere shape, and it's going to hold 2 electrons. Then the next shape is a P shape, which is shaped like a dumbbell. So we can call it a P shape or a dumbbell shape. And again, it's going to hold 2 electrons in this area. So maybe there's 2 over here, maybe one's on each side, but within this total dumbbell shape, we're going to hold 2 electrons. Every single orbital individually will hold 2 electrons. So the thing about the dumbbells in an energy level, once we start adding dumbbells, we can have up to 3 of these in one energy level. So if we can have 3 of these shapes and each one holds 2, that's going to give us the dumbbells holding a total of 6 electrons. The third shape is called a D shape, and these are known as double dumbbells. So you have 2 dumbbell shapes put together. So if I have 1 dumbbell, it's going to look like this. And so within these 4 petals, there is going to be a total of 2 electrons. And I can have up to 5 of these in one energy level. So if I can have 5 and each holds 2, that gives me the dumbbells holding up to 10 electrons. And then the last shape, the F shape, which this is kind of like a double dumbbell shape, but there's not really a name for that. Sometimes it's like the flower shape. So the F shape can again hold 2, and we can have up to 7 of these. So if we have 7 and they're each holding 2, we can have 14 electrons held in the F shape in one energy level. The next quantum number is the magnetic quantum number, and this just depends on how many different ways can we turn those different shapes. So if we look at the sphere shape, if I turn this sphere, it's not going to look any different. So there's only one possible orientation for the S shape. So we can only have one S shape. And this kind of goes back to those, how many we can have in an energy level that I was talking about. So the P, we can turn this 3 different ways. We can have it oriented on the x-axis, the y-axis, and the z-axis. So we can have 3 possible P's. We can have 5 D's and 7 F's. The last quantum number is called the spin quantum number, and this is designated by either +1/2 or -1/2, but this really relates to which way the electron is spinning, clockwise or counterclockwise. And if we think about this, they're like magnets. They're negatively charged. So if we have 2 negative magnets that we try to put together, they're going to want to repel each other. So with electrons, we have to spin them opposite ways so they won't repel each other and knock each other out of the area. So when we put these electrons in, one has to spin positively and one has to spin negatively. So now let's relate this to the periodic table. So there are 4 different blocks on the periodic table. So the yellow is designated the S block. And then we jump over, in this red area is the P block. Then the blue is D, and green is F. Now helium, he's kind of a little awkward guy. So he really kind of fits in this where there's a blank spot. He really fits in the S. And what all this means is as we go through the periodic table, we're adding electrons. If I were placing 1 electron at a time in an atom, and the last electron I placed for, let's say, oxygen, will be placed in a p orbital. Or if I'm looking at cobalt, the last electron I would put into cobalt, since it's in the D block, would be in a D-shaped orbital. Or maybe I look at californium. The last electron I would place for californium would be in an F-shaped orbital. And so kind of keep this in mind. You may want to somehow highlight your periodic table or mark on it, draw boxes so you know these blocks, because that's going to be important down the road. Another thing, when we talked about how many different shapes you could have. So if we look at this, we said we could have 3 P's, right? And so if each of those can hold 2, 3 times 2 is 6. 1, 2, 3, 4, 5, 6. So the block is as wide as how many electrons fit into that shape. So D's can have 5, and if each of those had 2, that's 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. S's, we can only have 1, and if each of those hold 2, it's 2 wide. F's, there are 7. Each hold 2. There are 14 elements wide here. So if you can't remember how many D shapes can I have, if you just count across the block and divide it by 2, you'll know how many D's you're allowed to have. We're going to use this simulation to try to kind of get a better visual of what's going on with these orbitals and energy levels and electrons. So first of all, they're telling us we're using helium, and helium is atomic number 2, which is 2 protons, but we're dealing with neutral atoms at this point. So if there's 2 protons, we're going to be dealing with 2 electrons. So a couple of things to keep in mind. The big number is going to tell us what energy level we're dealing with, and we have to fill up all of the orbitals in an energy level before we can go to the next one. Each orbital shape can hold 2 electrons. One rule we haven't talked about yet, but we'll get to in the next section. If I've got multiple orbitals of one shape, for example, we've got 3 P's here, we have to put 1 electron in each P before we can put the second one. So that's something we're going to come across, but we really haven't talked about yet. So as we start, helium, it's in the first. We're going to start off with the first energy level, and n equals 1 can have 1 shape, so that's a S. And so then we're going to put 2 electrons in there because each orbital holds 2. And they have designated here those electrons with arrows, up and down arrows, to indicate the spin that we talked about. So up's going to be like clockwise and down will be counterclockwise to show that they're spinning different ways. So we've got 2 electrons in there. We can see it here, or maybe we can kind of see it there, but we know we put 2 in. That's how many we needed, so we should be done with helium. Now they've given us carbon. So for carbon, we've got 6 electrons. So our first energy level is an S, and it's going to hold 2 electrons. So 1, 2. We've got our up and down. So then, since we're filled up in the first energy level, now we have to do the second. So we've got another sphere, but notice it's bigger because it's a bigger energy level. So we have to put 2 electrons in that sphere. So now we've used 4 electrons. And now we're going to start adding P's. And I put 2 on there because remember I said we have to put 1 in each P before we can double them up. So we've used 2, 4, 5, 6 electrons. And that's how many we needed. So we should be good. So check. And that's right. Now we've got sodium. So we need 11 electrons. So we're going to fill up our first energy level with 2. Then we're going to put our second energy level, our S. We'll put 2 in there. And now we can start adding our P's. So we're going to need all 3 of them this time. And notice they're going in different directions for those different orientations. So we've used 4 of our 11. So we're going to put 1 in each. 5, 6, 7. And then now we can go back and double up. 8, 9. Oh, let's see. How can I get it in there? I know. Where's the one I need? There we go. So I've used 2, 4, 6, 8, 10. But the second energy level only has S's and P's. Now I'm ready to go to that third energy level. So I'm going to start again over with my S. And notice that it's bigger because we have a bigger energy level now. So I'm going to put 1 more electron. And that should get me to my 11 that I'm looking for. So 2, 4, 6, 8, 10, 11. And now we have 18 electrons. So we know that all of the first and second is going to get us to 10. So 1, 2. I stop there. If I stop here and I've got 3 electrons, if I look at the periodic table for number 3, this would be lithium at this point. But I'm going to keep going because I want argon. Now I'm going to add my 3 P's. Fill those up one at a time. So I've got 1 in each. Now I can go back. 1, 2, 3. So now I'm at 10. Up to my, up to my next level. Fill up my S's. So now I'm at 12. Add my 3 P's on there. So notice again, they're bigger because we are in a higher energy level. 1 in each. 1, 2, 3. So we're at 12, 13, 14, 15. Now we can double up. 16, 17, 18. So these would be where all of our electrons will be located for argon. And that's right.